Hi guys. Okay, so today what we're going to talk about is what's known as momentum. And I'll talk about what that is, how it kind of relates to force, why it's useful, and stuff like that. Okay, cool. That's a good size. So momentum and collisions. First of all, let's define momentum. So what is momentum? Momentum has been defined mathematically as mass times velocity. So it's given the symbol P for impetus, and the fact that, m's been taken. Okay. It is a vector, unlike energy, which we've recently done, because it's defined in terms of a vector. So remember again that if something is going to be a vector, if you're defining something else in terms of the vector, there's a very good chance that it is also going to be a vector. So momentum has direction. Okay. Its units, because it's defined in terms of mass and velocity, will be the kilogram times meter per second. Okay. So how do we actually make this useful? Well, we can talk about, so I've just defined it right here as mass times velocity, right? So to make this useful, let's talk about, so how can we study motion with this? Well, if you remember, all of motion is kind of built upon Newton's second law. So all or at least the study of, all of the study of motion is built upon Newton's second law, which, if you remember, if you can get the sum of the forces, so you sum up all the forces, with the free body diagrams, right, you can get the acceleration of the object. If you can get the acceleration of the object, you can then understand everything you need to about its velocity and position from that point on for all of time. And that's really useful for us in this class, right? So what we can do is we can use this definition and relate it to momentum. So let's rewrite Newton's second law. Okay. So we get something useful out of it. So we still write it like this, right? But now what we can do is, if you remember the definition of acceleration, right? The definition of acceleration is the change in velocity over the change in time. So what we're going to do is we're going to plug that in over there. And now what we can do is we can adjust this and we can move the delta out. And what that means is we're not only going to allow the velocity to change, but we can also allow the mass to change. And this will allow us to do like a greater deal of problems that we couldn't before. Because if you remember, everything we've done up to this point, the mass has mostly been constant. And for this class, we're going to pretty much keep it the same way. But for derivation's sake, we are going to move this guy out. So now we have this written, okay? And if you remember, right, mass times velocity is literally momentum. So now we can write Newton's second law in terms of momentum, okay? So this right here is the, I guess, the best version of Newton's second law, the most complete. The most complete version of Newton's second law, because it allows mass to vary. So you can do stuff like rocket problems, where you could figure out maybe the force on stuff if you're changing the mass of the rocket, right? So you're seeing how the momentum changes or how the mass times velocity changes, right? And how that influences force, okay? So it's pretty important. This is the most complete version, more so than the more famously written equation. But of course, both can be useful for their own respective problems. So now what I'm going to do is I'm going to use this, use Newton's second law here, written in a different way to talk about another property. So now let's use this new form to define another new quantity. Okay. So we've got force over here, we've got change of momentum over time. If I multiply this guy over, and I write it in terms of momentum, we now have this new strange thing, force times time, force times change in time, right? The sum of the force, okay, times the change in time, equals the change of momentum of an object, okay? And this new property here is known as impulse, okay? So impulse, what impulse is, usually has I, okay? It's a vector. Impulse is defined as, so impulse can be thought of as some force acting on an object over some length of time, okay? And this is, for this stuff, it's usually pretty small. Okay? And that equals the change in momentum of the object, okay? Over some length of time. And so you must be wondering, well, how is that useful? Well, if you think about it, everything that we've done so far, we haven't really, we've done it kind of a little bit in tangential ways. We've talked about, with regard to forces, we've talked about just applying a force in a specific direction, but nothing else about that force. So we haven't really talked about, you know, the time that you apply that force or something like that, right? And if you think about it, how you apply the force matters. It's not just the direction, it's the duration. Okay? And so impulse kind of helps us talk about those types of problems. But more than that, impulse helps us talk about problems or are able to solve problems that are literally impossible to do otherwise or very, very difficult. So what I mean by that is, so this is most useful, I would say, for problems with forces that are applied to objects that distort or temporarily change the object during the force application. Okay, this is extremely complicated. So what I mean by that is if you're compressing, or so like i.e. compression or stretch of an object, maybe like the most famous example for this would be a bat and a ball. Is the de facto, the main example here that you usually see. And the reason for this is, you have a bat, okay, and a ball's coming towards it. And what happens is when this bat collides with the ball, okay, so that's really the key here, collisions, hence, the name momentum and collisions, right, for the lecture. So let me just write it up here. So collisions, okay. Yeah. So, or certain types of collisions. So this ball will hit this bat, and during, if you see like a camera that can film it at like, an absurd number of frames per second, what you'll see is that the ball and the bat, they both go through like, compression, and they change, right, while the force is being applied. If you were to try to just do that with Newton's second law, the computation time would be very, long. It would be very challenging to pull that off, to look at what's actually going on during the collision. But if you examine the momentum of this ball before the collision and the momentum of the ball, is a very, very garbage bat. The momentum of the ball after the collision, right? So before and after, you can get a lot of information about what occurred during the collision, okay? Or at least the parts you care about, I guess. Because most of the time, right, if we're examining this, we're going to look at the motion of the ball beforehand and we're going to look at the motion of the ball afterwards. That's what's most important. And we can use momentum and impulse to do that. So the bat, the way you look at this is the bat applies impulse to the ball, because beforehand the ball has this momentum, right, coming into, it has mass times velocity in a certain direction towards the bat. That's its momentum. The bat then applies an impulse which changes the ball's momentum, thereby changing its direction. Okay, and if you were to try to examine this, you were trying to figure out how the ball will move or whatever, the momentum of the ball or whatever, the motion of the ball after the collision due to what's going on in the collision, during that short time frame, right? Because a bat hits a ball. That's why this is the best example of this. It's a very small time frame, right? That the impulse is applied, right? If you were to look at this during that, it would be very, very challenging. And so what we do is we just look at the momentum before and look at the momentum afterwards, okay? And then we can figure stuff out from there. So we kind of just, it's kind of like when you're dividing by 0. You examine the graph around it rather than what's occurring at it, which is impossible, okay? So that's why this is useful, okay? Looking at these new terms, impulse and momentum, okay? You can also think of impulse and momentum as similar to work and energy, where you apply work into a system that increases that system's energy, okay? Similarly, impulse, an external impulse to a system changes that system's momentum, okay? Very, very similar concepts in how it works. So, let's just write this out here. So the system above shows a bat applying an impulse to a baseball, changing, or which changes its momentum. Okay. All right. So that's concept number 1, momentum and impulse. Concept number 2 is momentum conservation. Okay. So this is similarly to energy conservation, right? We can conserve momentum in collisions, okay? And actually, in problems, you're able to conserve momentum all the time, but you're not able to, in some problems, depending on how it's written, conserve energy, right? Like if you're losing energy in a problem and they don't tell you where the energy's going or what's causing that, you're not able to solve it with energy. So these problems, you're usually able to, you can use momentum for pretty much all of it. So let me go ahead and show you what's up. So why is there momentum conservation? With energy, there was energy conservation due to just the fact that, I ended up not deriving it in that particular video, but that was mathematically, you could show that, right? And so here, that's what we're going to do too. So, and I mean, conceptually, you can see why as well, right? If a system has a certain amount of energy in it, where would the energy go if it were to just vanish, right? The same thing conceptually you can imagine here, but mathematically, let me show you what's up and why it kind of stands on its own 2 feet. So here you want to imagine 2 particles colliding. So this is very generic. You can think of these as like, I don't know, 2 protons or even 2 balls or whatever. It doesn't really matter. So we'll say there's ball 1, it has mass 1, and it has a velocity. Okay? We've got a ball number 2 with the second mass, and it's also got a velocity. And as you can see, they're going to collide. Okay. So, they collide, right? And because they're colliding, they exert a force on one another, okay? Well, if you remember back to forces, we talked about 3 laws, right? Newton's second law we already talked about this time. The first law was just about, objects keep doing what they were doing before if you're not exerting a force on them. And then the third law is the one we're going to talk about, right? So due to Newton's third law of motion, the force they exert on each other is equivalent, okay? Right? Different directions, but mathematically equivalent. And because it's a collision, the time that they interact is the same, right? It's not like the time changes for each object depending on the collision. So the time they interact is also the same, okay? So because of this, right, if we look at the force on object 1 by object 2, okay, so that's the first particle. You have the second particle hitting the first one, and it's time, okay? Change in time, that's impulse, right? That would be equal to mass 1 times velocity final minus, or here, let me write it like this. First. That would be equal to the change in momentum of particle 1, which is, which would be the final velocity minus the initial velocity, okay? Which is change in mv, okay? And then the force on particle 2 on 1, okay, we can do the same thing. Forgot to give these guys vectors. Okay. And so what we're, therefore, to conclude, what we can say, F12 delta t equals the negative F21 delta t, okay, from Newton's third law. And if we plug this in, m1 v naught v1 naught equals negative m2 v2 final minus m2, sorry, I have to get all the subscripts right, gotta focus. And so what we can do then is we can apply this minus sign, minus m2 v2 final plus m2 v2 initial, okay? And so now what we can get is we can rearrange this. So we have the positive right here, m1 v1 final, okay, right here. This guy we can add over m2 v2 final, okay, so I added that guy over. This one I can add to the other side. We get m1 v1 initial plus m2 v2 initial, okay. So we've got our finals and our initials on their respective sides. And so what we can write now is P final equals P initial, or if you rearrange it, momentum initial, so initial momentum equals the final momentum in the system. So the momentum doesn't change, okay? So keep in mind though, there's no external impulse here. There's only the impulse between the two particles. They're each imparting their own impulse to one another. So what we will say, thus momentum is conserved in the absence of an external impulse. Okay? And that, again, that's similar to work and energy, where you can say in the absence of external work, energy is conserved. Okay, so similarly to in the absence Okay? So, that's basically momentum conservation. Okay, so far, all we've learned, we've defined momentum, okay, mass times velocity. We have talked about impulse. We use the momentum definition and Newton's second law to get a definition of impulse, which is just some force acting over usually a very small time. We talked about why that's useful, and then we said that there's momentum conservation. So now that we're basically saying, you know, this stuff is useful for collisions, let's learn the types of collisions. So what collisions are there? So there's types. And it turns out there's usually 4 that people typically have in physics books. The reality is there are multiple types, okay? And they all have varying degrees of elasticity. We'll talk about what that is, okay? In this class, I'm just going to talk about 2. Okay, so just 2 only. So, there's inelastic collisions, okay? Which I'm defining as collisions that take place that have friction, heat, deformation of the object upon collision, okay, etc. Okay, so there's some loss there, okay, is an inelastic collision. Just like with energy, right? If there's friction involved, right, you're losing energy to whatever that non-conservative work is. So you can think of inelastic collisions as just the analog to non-conservative work. Okay. Elastic collisions, so completely elastic, is usually what I'm going to focus on. So completely elastic or fully elastic or whatever, 100% elasticity. None of the above, okay, take place during the collision. Okay. So you're not losing heat. There's no friction. It's completely elastic, like rubber balls. Okay. So you can think about this as like usually it'll be defined as like just like rubber balls. For the record, there's probably nothing that's completely elastic in the real world. There's always some degree of loss, right? Like even with 2 rubber balls, if you drop a rubber ball onto the floor, it's not going to reach the same height as it would have before. A couple things I should say. Inelastic collisions only conserve momentum, okay? So you can still conserve momentum there, but you can't conserve, we'll talk about it, energy in terms of kinetic energy, okay? Completely elastic collisions can conserve both kinetic energy and momentum. Okay, and you'll see that actually makes the problems more complicated. Because kinetic energy is 1/2 mv squared, right? And that v squared is actually usually pretty complicated. So I'm going to go ahead. I'm not going to derive this stuff for you, but not going to derive it for you, the final elastic equation for you, because it's fairly long and there's a lot of math there. But you can do it if you want to. And I can show you if you want me to. Just let me know. So 1D equations. So there's two types where we're basically going to examine like balls just coming in and out. That's on a one-dimensional plane, fully in the x-axis. But there are also 2D problems. But because these are vectors, you can imagine they get complicated. So M1, V1, O, M1, V, so this is initial momentum of the first object. 1D equation for collisions. Okay. So M2 V2 O equals M1 V1 final plus M2 V2 final. So you have to have subscripts on everything because the masses might not be the same, right? You might have varying ball sizes, right? Like a big ball, a small ball. And the velocities also can vary, okay? So this is for collisions for both inelastic and elastic. The second one, oh, this also has dropped vectors because you denote it with positive, negative for 1D. So dropped vector symbols use plus minus to denote direction, right? Because you can only move in, one direction, right? You can either move to the right or to the left. So you really only need plus minus for that. The other equation that you can have here, 1/2, so this is the first ball's kinetic energy. The second ball's kinetic energy, and that would be equal to the final. Okay, like I said, there was kinetic energy conservation for elastic collisions. So this is what this means, okay? So this is for elastic collisions only. Now again, this can be rewritten because this is a lot. V1, you can basically cancel the masses. This is in certain situations only. But for elastic collisions, because I'm telling you elastic collisions are really, really complicated to solve, because you can imagine, if you're using both of these equations, and in one of them it's squared, elastic collisions, 1D even, and 2D is nuts. Elastic collisions are really, really challenging. So I usually limit that to where you can use the second equation. But I'll show you how these work, okay? So this is, again, Scholastic only. And I think on the stipulations. Okay? But this guy right here, this equation, this first one, can always be used for sure. This one, I'm pretty sure it can be rewritten. The only stipulation here is that the masses might have to be the same. So, okay. So 2D equations work similarly but since they are vectors, there are both x and y equations. So you have to conserve momentum in both dimensions. Okay, so it's pretty challenging to do that. But I will talk about that in the examples video. Okay, so for that we've got 1, 2, 3, 4, 5, 6, 7, 8 examples of momentum. Okay, but I will do that in that video. So thank you guys for watching. And I'll see you in the next one.